So, welcome all of you in continuation of the lectures on properties of nucleus, their mass and their stability. So, that is the theme for us. So, as you can see on the slide, I have again written masses and stability, which is probably the third in the series of our lectures. So far our analysis has been rather qualitative, and we have not used numbers to a great extent. We have not analyzed things in a quantitative manner. Today what I shall do is to show that even at our level, 12th standard level, it is actually possible to draw a large number of conclusions and in fact attain a large number of consequences, understand a large number of consequences and also appreciate physics at the cosmic scale. For example, what is happening inside the sun simply by looking at energetics, energy conservation, the associated masses and of course the famous relation E equal to mc squared, which follows from special theory of relativity. So, that is something that we should know. So, in that sense today's lecture covers an extraordinarily important topic because we are looking at an object of the order of 10 to the power of minus 15 meters, 1 femtometer, and we are going to work out the consequences of something which is of the order of 10 to the power of plus 15, let us say, that is whatever are the processes that are happening inside a star. At the end of the lecture I will also tell you that whatever we study about the nucleus also sheds very important light on the dynamics of our own planet, the earth itself, which has been quite a mysterious object for a long time for physicists and geologists. I will also be able to make such a statement. So, the message that we are trying to convey is that although we are studying one particular phenomenon at one particular length scale, which is very tiny, microscopic, which is even smaller than an atom, the ramifications can be enormous and can extend to very large areas, which tells you actually how the unity of physics is all pervading. You understand one thing, you understand a whole lot of things. In fact, the same thing happens even in atomic physics. Once people understood the atomic spectrum through the Bohr model, they were able to understand, appreciate the constituents of the sun, because there is helium, there are these atoms and there is a temperature because of which the atoms gets excited and they get de-excited. So, what you do is to conclude what is the composition of the sun, at least the surface of the sun, the photosphere let us say, by studying atoms in your laboratory. That is one of the great achievements. We are going to show a similarly great achievement or a triumph of physics today by looking at some very simple properties which I have already listed. So, just to set the ball rolling, let me repeat a few things for you just to warm up. Nuclear forces are really interesting because they are independent of electrical charge. So, the interaction between the proton and a neutron and a neutron and a neutron and a proton is so strong that you can practically forget electromagnetic forces. Of course, you cannot completely forget them, I will come to that again, but for all purposes, most of the purposes you can forget about them. So, the interaction is very strong. It is typically about 100 times stronger than electromagnetic interaction, and of course, it is very short range. Whereas, electromagnetic interaction is of an infinite range. What is the potential between two charged particles? So, if you look at, for example, the electromagnetic interaction, if you put two charged particles, the potential between them is given by E squared by R. I am assuming that both of them have the same charge. So, this is what we mean by an infinite charge. It is a kind of a very smooth polynomial which is decaying as the first power of the distance. Whereas, if you look at a proton and a proton, let us say, or a nucleon. So, let me show you a nucleon. What would be the corresponding potential between them? This would look more like, apart from the strength, I will call it as lambda, e to the power of minus mu r by r. This is called the Yukawa potential. It is also called the Debye screening, which you will encounter, for example, in electrolytes. We will encounter the same interaction even in plasma physics, or for that matter in dielectric materials. So don't think it is something peculiar to nuclear physics. And the important point here is that apart from this 1 over r potential, so V of r is what we are writing. Apart from this 1 over r potential, there is a fast exponential fall. So if I put mu equal to 1 over r, you will see the potential falls to 1 over r of its value. So what are we saying? At very, very short distances, e to the power of minus mu r is very close to 1. So that is the interesting thing about this curve. So I am writing V nuclear of r is some strength lambda e to the power of minus mu r by r. So for r very small, what do you mean by r very, very small? By that we mean mu r is very small. R is not a dimensionless number, so it is meaningless to say distance is small or large, but mu r is dimensionless number because mu has the inverse dimension of length. So if mu r is very, very small, then e to the power of minus mu r approximately equal to 1. So for mu r very, very small, my potential behaves like 1 over r potential, but for mu r very, very large, so mu r much, much greater than 1, you see this will go to 0 much more rapidly than r goes to 1 over r goes to 0. That is what we have, and then we say this potential is screened, and we say the range of the potential mu is the range of the potential, range of the interaction. Mind you, what I have written is the potential. You can always find out the force corresponding to this by differentiation with respect to r by putting a minus sign, minus dV by dr. I will leave that as an exercise for you people. So when I say that the nuclear forces have a range of a femtometer, 10 to the power of minus 15 meter, basically we are saying that mu inverse is 10 to the power of minus 15 meter. That is the precise statement. You should not think that is something like a step function. It is constant up to 10 to the power of minus 15 meter and it is going to come down. That is not what is going to happen. So this is precise meaning of what the short range is, and with this what we want to do is to combine whatever we have got with the mass defect idea and obtain some insight, some appreciation of the dynamics that is going in the interior of the sun. That is our great purpose today. So let me go on to the next slide. So we have to start with some illustrative data which I have already calculated, and this is an exercise that you can do by opening up the periodic table or the so-called nuclear data book, which will give you all the masses and of all the nuclei with their isotopes, isobars, whatever nuclide you may be taking. And here is an illustrative data where I am comparing the masses of proton, neutron, helium. Is that okay? Remember, my helium consists of what? 2 protons and 2 neutrons. Therefore, what I am interested is, I will find the combined mass of 2 protons and 2 neutrons. I will find the mass of the helium nucleus and I ask, are they going to agree with each other? What would Mr. Newton tell you? If you people remember, in your 10th standard, 11th standard, or even probably even earlier, you were told there is a mass conservation, there is an energy conservation, there is a momentum conservation. That is what you always assume. When you solve problems in dynamics, that is exactly what you do. Let us say 2 particles come, they collide and they go. You don't say that the mass of the incoming particle has changed. A ball goes and hits against a wall and it gets rebounded. The ball has a mass m before and after collision. Nothing is going to happen because total mass should be a conserved quantity. But relativity tells us that mass is not a conserved quantity, only energy can be a conserved quantity, because total energy can be conserved because mass can become energy and energy become mass, and with every mass there is always an associated energy which is given by mc squared. That is something that I told you repeatedly in the previous lectures. Now what I want you to do is to pay close attention to that and look at these numbers. So let us start looking at these numbers. Please notice that I have taken care to write the numbers to a large number of decimal places. That is not because I have a calculator and I can calculate it up to that decimal places. All of you have studied something about significant digits. What I am doing is actually to employ the masses to the required number of significant digits. So this gives you an idea of the accuracy and the precision with which these masses are determined. So if you people become physicists, you will appreciate it even much better, how we keep on pushing the frontiers of how well we know the values, and that itself requires deeper and deeper understanding of physical laws. So if you look at the mass of the proton, which we already know, we are working in the units of atomic mass units. Remember, how do we define the atomic mass units? You look at 12 carbon and to declaration, because that is my standard, declare that its mass is given by 12 atomic mass units, and with respect to that you fix the masses of every other nucleus and every nucleon also. So if you remember that mass of the proton is given by 1.007276 atomic mass units, mass of the neutron is 1.008664 atomic units. Something that will be important for us at a later time, although I have already told you, is that my neutron is slightly heavier than a proton. Chadwick in his great experiment argued that they should be roughly of the same mass. Today precision experiments tell us, of course they are roughly of the same mass, but neutron is slightly heavier than the proton. When I am going to discuss beta decay for you, this is something I am going to concentrate upon, because a neutron decays by emitting an electron and an antineutrino, and it decays into a proton. That is something that is important. And of course I am interested in the mass of the helium atom, and mass of the helium atom is given by 4.002602 atomic mass units. So that U is my atomic mass unit. So what is it that I am interested in? I am interested in the difference between the daughter and the parents. What are the parents? The parents are the 4 nucleons, 2 protons and 2 neutrons. So the 4 parents came, they joined together to produce a daughter, which is the nucleus. That is the jargon that we are looking at. So what do? I look at the mass of the helium atom, I look at the sum of the proton mass and the neutron mass. There are 2 protons, there are 2 neutrons, that is what I have. So this is minus 2 of mp plus mn. When I do that, lo and behold, what is it that we have? What we have is that this difference is not equal to 0. In fact, it is negative, minus 0.0292728 U. That is very important. What does it mean? Associated with this mass defect, there is an energy, delta mc squared, and that turns out to be minus 28.3 MeV, million electron volts. In the atomic scale, your energies were of the order of electron volts. In the nuclear scale, your energies are of the order of million electron volts. Why is that so? In a way, you can understand it from the uncertainty principle. An atom is confined over a distance of 1 angstrom, so delta P, delta X, whereas a nucleus is confined over a distance of 1 femtometer. The order of magnitude difference between them is about 10 to the power of minus 5 or 10 to the power of 5, depending on which ratio you are going to take. Okay? Therefore, the corresponding energy scales here are all given by MeV. So what does this relation tell me? This tells me that if I want to break a helium nucleus, and separate them into 4 constituent nucleons, how much energy should I supply? I should supply a very large energy of 28.3 million electron volts. That is the most important thing. In order to break the hydrogen atom, I was supplying something like 13.6 electron volts. So, for example, if I keep on heating hydrogen atom, is that okay? At some temperature it will ionize, it will become a plasma. And that temperature is something of the order of, let us say, 10 to the power of 5 Kelvin. Because 1 electron volt corresponds to about 10 to the power of 4 Kelvin. You know E is equal to kT. All that you have to do is to substitute that formula. But here you have million electron volts. That is what I have. So what are we saying? So here is a good thermodynamic exercise or a kinetic theory of gas exercise that you can do. So what we are saying is that if I write E is of the order kT, I want to boil helium nucleus to completely dissociate. This is the it into 4 nucleons. That is what I want to do. So what is the binding energy? My binding energy is of the order of 30 MeV. Now I am not interested in the precise numbers. We will get back to the precision numbers later. And in order to supply 1 electron volt of energy, you need about 10 to the power of 4 Kelvin. So what are we saying? For example, if you are saying if you have a monoatomic gas and it is at 10 to the power of 4 Kelvin, let us say, then the energy carried by that atom is of the order of 1 electron volt by equipartition principle, by substituting the Boltzmann law. Therefore, if I have to supply 30 MeV, what is the energy that I need? So this is 10 to the power of 4 into 10 to the power of 6 into 3. If you feel like, do not worry about that. You have to go to 10 to the power of 10 Kelvin. So that means that if I just want to make a soup of nucleons by heating helium atom, let us say, then your ordinary furnaces and heating instruments in your lab are not going to help. Is that okay? You get very, very high temperatures for smelting the ores, for example, in your metallurgy labs, but they are not going to help. In fact, we do not have such a natural temperature anywhere on the earth, not even deep inside the earth. Is that okay? So if you want to attain temperatures of this order, if you want to break it, you should be able to actually go somewhere where such a temperature is naturally available. But that is not of interest to us. What is of interest to us is the other way around. Okay? And that requires a different temperature altogether. I will come to that, but this is something that you have to remember at this particular point. So what I will do is, I will now I will come back to this slide and get back to 28.3 MeV, and let us move on to the next slide. What we are going to do is to make use of this 28.3 MeV and unlock the doors to the secret of the solar energy. At some point when I was introducing the Bohr model, or for that matter even the Planck hypothesis, I told you one of the great mysteries which 19th century physicists faced was, how is it that sun is able to produce such an enormous energy? Okay. Now there are some numbers which you have to remember. Our earth is about a few billion years old. That means sun must also be of the same order. In fact a little bit older, if you assume that the planetary system was formed at some particular time. So if the sun has to be burning for a billion years, is that okay? Where is the energy going to come from? At that time, people knew nothing of atoms, people knew nothing of nuclei, people only knew thermodynamics very, very well, which we are also going to use right now. And the only source of fuel that they knew was the burning of coal. So the great Helmholtz made an estimate and said that, I know the temperature, I know how much energy is radiated from the surface of the sun. They did not know anything about the interior of the sun either. Is that okay? So he estimated that the sun would not last for more than 5,000 years. But we know sun will last for much, much more time. So that was one of the great mysteries. Is that okay? So now whatever you have learned, however little it may be from the viewpoint of physics, because you have been just given some numbers, you can still get an understanding, an appreciation of what is happening inside the sun. And that is the reason why I am saying we are now going to unlock the secret of solar energy, and I am going to spend a fair amount of time going very, very slowly. Is that okay? So that you people get an idea, because in doing that, not only do we understand the physics, there are also other things, conservation of charge, conservation of lepton number, conservation of energy, etc., etc. So all those things I am going to keep showing you, so that later when you look at problems, when there is a nuclear decay and all that, you know how to balance. So we actually shoot two birds with a single stone. That is the thing. So what is the secret of solar energy? The idea is that the two hydrogen atoms are going to combine to give a helium atom. But before that, we have to ask a few questions, and that is the breaking of the Coulomb barrier. Okay. As I told you, I am not interested in boiling a helium nucleus. I am actually interested in producing a helium nucleus. And in producing the nucleus, there will be a lot of energy that is generated, and that energy that is generated will be responsible for the sun to glow so very nicely, because that is what is going to convert it into heat, and then my thermodynamics, there is going to be a radiation that is emitted at that temperature, the Stefan-Boltzmann law. That is what I want to do. So what I want to do is to bring 2 protons plus 2 neutrons to form the helium. So 4He2. So one notation that you people should remember at this particular stage is that I have already used it. Sometimes we write it as 4He2 and sometimes we write it as 4He2. It doesn't matter. So sometimes we write as AXZ and sometimes we write as AXZ. They are identically the same. So please remember that. What is it that we want to do? We want to bring forget about the neutron, because neutron is not electrically charged. So if I have 2 protons and if I want to bring them together, there is also a neutron, there is also a neutron which I want them to bring together. If the distance between the 2 protons is of the order of 10 to the power of minus 15 meters, 10 to the power of minus 15 meters, all distances are of 10 to the power of minus 15 meters, then we know that they can form a nucleus. That is the whole idea. But the problem is, how do you bring them this close to each other? Because there is a Coulomb repulsion. This is repulsive equal to, so I am going to write E squared by R. That means you have to supply an enormous energy in order to bring them together. So if indeed the energy produced in the sun is because of the nuclear fusion, there must be a corresponding energy. So this energy should be equal to the kinetic energy. When the kinetic energy corresponding to kT, I don't have to worry about 3 by 2 and all that, corresponding to R equal to 10 to the power of minus 15 meters. So somehow if I can impart a kinetic energy such that kT equal to E squared over 10 to the power of minus 15 meters, that is the number that we are giving, then they can come that close, and once they come that close, the strong interactions will take over from the electromagnetic interactions, the Coulomb interaction, and then we can worry about the strong forces. A simple exercise that I would ask you people to do is to estimate the temperature, and the temperature turns out to be something like 10 to the power of 10 Kelvin. I am not very sure of this number, it could even be 10 to the power of 11. I don't know. So I will be a little bit more careful and say 10 to the power of 10 to 10 to the power of 12 Kelvin. So something of that order. But how do I get this number? You get this number by assuming an ideal equation of state, PV equal to RT. Remember, you were actually able to obtain the relation PV equal to RT starting from kinetic theory, assuming that there is no interaction, there are only collisions, etc., etc. But in the interior of the sun, actually it is much more complicated, because there is going to be a lot of pressure apart from the temperature itself. Is that okay? So if you look at the interior of the sun, the temperature in the interior of the sun, core of the sun, maybe it is in a slide, is of the order of 10 to the power of 6 to 10 to the power of 7 Kelvin. So what I am trying to tell you is that a naive estimate gives you about 10 to the power of 10 to 11 or 12 Kelvin. But if you work out the equation of state more carefully and if you ask, oh okay, tell me what should be the energy, then the required temperature goes down and it comes to 10 to the power of 6 or 10 to the power of 7. There is nothing surprising in that. How do you bring two particles close to each other? Either you give them enormous energy or you keep on applying pressure. When you keep on applying pressure, the interparticle distance becomes smaller and smaller. So in the real scenario, in the real situation, both temperature and pressure play a role, so that the temperature is of the order of 10 to the power of 6 to 10 to the power of 7 Kelvin, and we are working in this particular regime. Now what you do is to work out the nuclear physics process, and the process is shown in this slide. Okay? So this is something that people worked out soon after quantum mechanics was established, and it is a great delight to see how it is happening. So the first step is that two protons, they form a 2He2. This is a diproton and it is a very, very unstable state. You should not think, because how can two protons be together? I told you that there is no bound state of two protons, there is no bound state of two neutrons, there is always a bound state of only one proton and one neutron, what we call as a deuteron. In other words, this is an intermediate state. This is not a stable state. Actually, I should put a star here. So it is formed for a short while, but before it splits, what happens? This 2He2, okay, that is exactly what is happening. It breaks into 2He1 plus a positron plus a neutrino. That is what it breaks into. That is what is going to happen. I am going to check that because there may be an error sitting here. So what I have is two protons is what I am going to have. I am very sorry for the error. So let us correct it. So let us leave one of the protons. So another proton will emit a positron plus a neutrino. That is what is going to happen, plus a neutron. That is what is going to happen. So the final state is something like this. 2p goes to p plus n plus positron plus neutrino, and this is nothing but your deuterium. So what I am trying to tell you is, when I was making this slide, I was not very careful, but no problem about it. I think the same error has crept into the next line also. This must be 2H1. Is that okay? One proton and one neutron is nothing but your this one. Don't treat it as He but an H, plus a positron plus a neutrino. And what is positron? Positron is the positively charged electron. It has exactly the same mass, same spin, everything. The only difference between a positron and an electron is in the charge sign, and then there is a neutrino. I want you to pay attention to this neutrino a little bit. Therefore, what is the overall result? As I told you, this is an intermediate state. The overall result is that two protons produce to form a deuteron. I am very sorry, this is not helium but a deuteron. This is incorrect. Plus an electron plus a neutrino, and this is the most important thing. It releases 0.42 MeV of energy. Here we looked at only the matter. We did not say whether the process is exothermal or endothermal. Endothermal means you have to supply energy. Exothermal means energy is given. This gives a 0.42 MeV, but then this process is very, very slow. Why is it very, very slow? Because if you come back to this slide, I have written that my proton goes to positron plus neutrino plus this one. Every time there is a neutrino, believe that it is something called weak interactions, and weak interactions, as their name suggests, are always weak, and whatever is weak, those processes take place very, very slowly. So this is a weak beta decay. That is what is going to happen. So this is a process. There is one more thing that you should notice at this particular point. I have written a positron and a neutrino and a neutron. My proton has a charge plus, my E plus has a charge plus, my neutrino is neutral, neutron is neutral. That means every time I write a process, not only is energy conserved, but what is conserved? What is conserved is also the total charge. mass is not a conserved quantity. That is something that you should remember. Because for all practical purposes, my neutrino is massless. If you add the mass of neutron and positron, it will not add to the mass of the proton. But total energy is certainly a conserved quantity, because these are not produced at rest. Actually, they will move apart. Is that okay? The total energy, the total rest energy of the proton, for example, if the proton decays at rest, will be shared among the energies of all the three particles. So this is a deuterium. What will happen for the positron? You don't see positron anywhere. Is that right? So just as Mr. Einstein tells us that energy can be converted to mass, mass can also be converted into energy. So that is indicated in this. What will happen? This positron, so this is indicated in this slide, this positron will encounter an electron. There are a lot of electrons inside the star, right? And they will immediately decay into 2 gamma, 2 photons, and in that process release an energy of 1.02 MeV. Is that okay? There is an energy, because the rest energy of each of them is of the order of some 0.5 whatever. So it releases an energy of 1.02 MeV. Now you see energy is getting generated. This is a weak process, whereas this is an electromagnetic process, and electromagnetic processes are always faster than weak processes, and strong processes are of course much faster. That is what you have. Okay. Now the next thing that happens is that my 2H1 will go to 3 helium plus a photon plus 5.49 MeV. I am going to show how the energy is produced in its successive stages. So I have not indicated the complete process there. So let me do that here. Is that okay? So what we are saying is that 2H1 is going to 3 He2 plus gamma plus 5.49 MeV. Now obviously there is a problem in this, because this means there is 1 proton and 1 neutron. And what do we have here? You have 2 protons and 1 neutron and a gamma. So what should the correct process be then? I should write 2H1 plus 1H1. That is what I should write. This goes to 3 He2 plus gamma plus 5.49. So if I were to use ordinary units, my deuteron plus a proton goes to 3 helium plus energy. I am going to go back to the binding energy table very soon. So what have we done? We started with protons, and through an intermediate process we were able to produce a deuteron, and this deuteron in combination with a proton will go to a 3 helium plus a gamma plus 5.49 MeV. This slide has omitted P, but never mind about that. We have actually worked it out and show you. Now this is not the end of the story for us. We are interested in the production of the helium-4, because helium-4 is the most stable in that neighborhood. That is something that you have to remember, and that happens through many routes, because our end point is actually the formation of helium-4. So the first route is this quantity. 3 heliums will produce a 4 helium, will produce 2 protons and an energy of 12.86 million electron volts. So what am I saying? If I come back to this, let me spend a few minutes so that you understand what is happening. 3 helium plus 3 helium, they come together. It produces a 4 helium plus 2 1H1, that is 2 protons plus 12.86 MeV. So all these processes are producing energies. So let us keep track of these things. So what are we saying now? This has 2 protons, 1 neutron plus 2 proton, 1 neutron is what it is. This goes to 2 protons, 2 neutrons. So 1 neutron, 1 neutron, 2 neutron, and this is nothing but your 4 helium. Then there are these 2 protons which are left, because total is 4. So, this is this 2p, this quantity is my 4 helium plus 12.6 MeV. This is the first route. So, if you look at this, I want you to concentrate on this. Here you have hydrogen, here you have helium, and here you have helium, and here you have lithium. So, and then of course you have your 12 carbon, let us forget about that, get concentrate on that. That means the immediate neighborhood of helium consisting of tritium, hydrogen and lithium, they all have less binding energy than 4 helium. That means once you go into 4 helium state, that is going to the most stable state. It is a different matter that 12 carbon is even more stable, 16 oxygen is even more stable, and iron is the most stable. We are going to come to that later. Nothing is more stable than iron, because that is the top if you look at the binding energy. Right now we are concentrated in the formation of helium. Therefore, if you supply the right conditions, then all these nuclei would like to go and sit in 4 helium state. That is your analog of your inert gas. That is the most strongly bound. It is a noble nucleus, if you feel like. That is what we want to do. So, we want the nucleus to sit in that state, and in that process, because it is the most bound, that means it requires maximum energy to be broken. That means when you are forming them, a lot of energy is produced, and that is what we are interested in. So, this binding energy per nucleon is a very important thing for us to study. Is that okay? So, let me come back to this slide, whatever we are looking at. The first route consists of 2 3 heliums. 3 helium 2 plus 3 helium 2 will produce a 4 helium plus 2 protons plus 12.86 MeV. Now, you have to do a addition, energy auditing, right? Like you put an electricity meter and it tells you how much energy you have consumed. Is that right? So, in a similar manner, what we should do is we should go back to the previous slides, 5.49, 1.02, 0.42. So, we have to look at an energy audit and we say, okay, if I give the right condition, what is the right condition here? The right pressure, combination of right pressure and right temperature, then my protons and neutrons will combine together to form helium and they will release so much of energy. Mind you, we are not speaking of energies of burning of a coal, which may be 100 degrees centigrade, 300 Kelvin. We are not looking at electron volts, which corresponds to 10 to the power of 4 Kelvin, 2 orders of magnitude. We are speaking of million electron volts, which corresponds to 10 to the power of 10 Kelvin. You get the point, right? 10 to the power of 6, 7 to the power of 7 Kelvin. So, that is the kind of energy that is produced, which can never be understood in terms of conventional fuel. What we need is the nuclear fuel, and that is what radioactivity, nuclear physics has taught us, and that is what we are looking at it very, very slowly. I told you that this is the first route. That means there are many, many ways of forming 4 helium. This is one of the ways, and there are other ways which we can worry about. But before we do that, as I told you, we have to do the net contribution. The net is, if you add up all of them and remove all the intermediate stages, like you do in your chemistry class. Is that right? There are intermediate things that you are going to form. For example, when there is a catalysis. So, it is somewhat like that, in right temperature or whatever. 4 protons and 2 electrons give you a helium atom plus 6 gamma plus 26.7 million electron volts. That is what you are going to get. That is, the synthesis of one helium atom with 4 protons and 2 electrons generates an energy of 26.7 millielectron volt, which is an enormous energy. So, this is the energy auditing. I am not going to worship for this number. I know that it is correct, but it is your responsibility to verify. When you add all of them, you indeed get 26.7 MeV. So, here is a cartoon which is picked up from Wikipedia, and whatever I showed you in terms of all these formulas, it has been illustrated in this. So, it is very, very nice. 2 protons, they emit a neutrino, there is this diproton, that becomes a 2H, 1H, again it produces a gamma, then it becomes a 3 helium. The same process is happening here. These 2 3 helium nuclei what happens? They emit 2 protons and they produce 4 helium. So whatever I wrote in equations has been shown here. Is that okay? So the red thing is a proton, this is a helium, and there is a neutron which is sitting there. So see, the neutron is sitting here. So this is something that is showed in a cartoon manner. Gamma, of course, always stands for the photon. So you can write these chain reaction processes. This is a case of chain fusion with emission of energy and a few particles. That is what you have. And this is an illustration. And as I was telling you, the most important thing here is not this figure, but this number. The temperature inside the core of the sun is 1.5 into 10 to the power of 7 Kelvin. So I repeat, when we were doing a naive estimate, we were getting a number of 10 to the power of 10 Kelvin, but then the pressure inside the sun is so very large. Maybe I have a number somewhere down the slide, even 10 to the power of 7 Kelvin will do the job, and this is the first route for producing the helium atom. Remember, when I showed you the binding energy curve, I was showing you lithium, and I told you even for lithium, the binding energy per nucleon is smaller than that of a helium. Physics exploits that, nature exploits that. So what happens in the case of the second route? We are going to start with a 3 helium. You have already produced a 4 helium. You produce a beryllium. Now I am not going to work out. You can see everything is matching. 3 plus 4 is 7, 2 plus 2 is 4. Because Z should add, A should add, N should add, you produce a gamma. This 7 beryllium 4, which is an unstable nucleus, it combines with an electron to produce 7 lithium 3 plus a neutrino plus 8.5, it releases 8.5 energy. This 7 lithium combines with a proton to produce 2 4 helium nuclei. So again you see 7 plus 1 is 8, 3 plus 1 is 4. That is 2 into 4 He2, 2 into 4 is 8, 2 into 2 is 4, and there is an energy that is released. This is the second route. There are 2 more routes. I am not going to tell you what they are because there is no point in spending time on all that. But the most important thing is we are interested in what is the total energy produced. This is now the energy audit, and this is something that you should know. What will you do? You know what is the how many protons are there, how many neutrons are there, how many electrons are there, and you know what the temperature is, and you know the radius of the core. So you make use of all these processes, compute how many fusion processes are taking place. Each fusion process produces this much energy, and then you find out whatever is happening, and this is something interesting. Radius of the sun's core is about 99% of the total radius of the sun. Now, what is the power generated? The power generated because of this fusion is 300 watts per meter cubed. It is very, very important. This number 300 watts per meter cubed is whatever is produced. And how many protons are burnt? That is how many protons are fused? 3.6 into 10 to the power of 38 protons per second, which is about 3 into 10 to the power of 9 kg of protons, that is hydrogen, is getting burnt per second. Is that okay? So that is a furnace which is of enormous magnitude, of enormous dimension. Is that okay? That is what is happening. And what is the total energy that is produced? 3.8 into 10 to the power of 6, 10 to the power of 26 joules per second. Look at the enormous number, which is about 10 to the power of 27 watt hour. So there is a nuclear reactor. What kind of a nuclear reactor is this? It is not a fission reactor, it is a fusion reactor. The nuclei are continuously fusing in that temperature. In that process, they are producing a lot of energy which actually sustains the temperature, and more fusion will take place. You know, it is a self-consistent, self-feeding phenomenon. And what is the percentage of power produced? Sun can produce power through other ways. This is the most dominant mechanism. 91% of the energy produced by the sun is because of this process, and just by looking at the nuclear stability curve and looking at the binding energy per nucleon by doing an experiment in the lab, we are able to understand what is happening in the interior of the sun. The great philosopher Kant said, of course physics was still in its infancy, we only knew Newtonian mechanics and planetary orbits. That itself was a great accomplishment. But the great philosopher Kant said that there are 2 things which moves him enormously. And what was that? The starry sky, in the heavens, and the moral order within the man. Moral order within the man is outside, the purview of physics. But whatever the starry sky we are seeing, stars, all the stars up in the sky that we are seeing, we are now getting a glimpse of what is the underlying physics for them to shine perennially, right? Almost perennially, because this is the energy. 10 to the power of 27 watt is what we are producing, which is 10 to the power of 26 joules per second. Now, in order to get an appreciation for that number, I want you to look at this curve. If it is not completely visible, which is possible, I can actually write those numbers for you. So, what we are interested is in total power generated by in earth by us on the earth. I should be very careful. By us, by humans. Is that okay? Now we are producing power through many ways. One is coal, then you have gas, then you have hydro, right? Then of course you have solar, that is becoming very popular. Then you have wind. If you go to Holland or some such countries, lot of energy is generated, for example on the seashore. Then you have oil, and then you have other fellows. Okay, nuclear, I should not forget that. And there is some percentage. Actually the maximum is because of the coal pollution, it is about 40%. Gas is about 23%, so on and so forth. And nuclear is of interest to us. Is that okay? Nuclear is 10%, this is not bad at all. There are a lot of nuclear reactors, I will show you what it is. So that is what it is produced. But how much energy is produced? That is the most important thing. Total power is about 25,000 watt hour, terawatt. The precise number is 24,345. So you have 2.5 into 10 to the power of 4 into 10 to the power of 12, which is of the order of 10 to the power of 16 watts. So this is the energy that you are producing. Is that okay? And how much is the sun? Go back and check what it was, you will find. So actually I can go back and check. So let us do that exercise. In case I have made a mistake, I can correct it. It is 10 to the power of 27. So earth is 10 to the power of 16, sun is 10 to the power of 27. So we are speaking of power sun divided by power earth is of the order of 10 to the power of 11. This is the enormous difference. Is that okay? And of course, we can never ever hope to catch up with it, which is completely impossible, because we are a mere planet and we are not a star. Although we are all formed of stars, because all nuclei are actually synthesized within the, where? All nuclei are synthesized within a star. That is what we are going to see in a while. So this is some number which you should be able to appreciate, and that is what we have. Now there is no reason for us to stop at this particular stage. We could actually go a little bit ahead and do a few more things, and let us see what we can do. Okay. For that, what I should do is to look at the binding energy table again. Actually I should have put it, but anyway, let us go back. You see, if you look at this binding energy table per nucleon, my helium-4 has very large binding energy per nucleon, which is about 6 point something, but carbon is even better. That is of the order of 8 MeV per nucleon. So given sufficient temperature, I should be able to actually even produce carbon, in which case even more energy will be liberated. But then there is a catch. What is the catch? So, let us look at the catch. The catch is the following. For helium synthesis, let us say a temperature T is required. I am only making an estimate, so let us forget about the pressure. For carbon synthesis, we need a temperature T prime, or I will call it T C and T H E. Now, my helium has 4 protons, whereas my carbon has 6 protons. So, you can make an estimate and you can find that to bring down 6 protons together requires much more energy than bringing 4 protons, sorry 2 protons, 2 protons together. So, if we have 6 protons, how many pairs are there? That is what we have to count. That will be 6. See, 2 pairs are there because each of them have to come close to each other. And what is this number? This is 6 into 5, 30 divided by 2, which is 15. So, you need at least an order of magnitude more of temperature. So, as you keep on increasing the temperature inside the core, that is the statement that we want to make, then you can keep on synthesizing higher and higher A nuclei until you hit iron. Iron will be the most stable. That does not mean that other nuclei cannot be synthesized, like molybdenum or whatever, W is tungsten, so on and so forth. But then this is the most stable one. Eventually this is the most stable one. All these will be in small quantities, there will be some metastable states or whatever, you do not have to worry. That is the lesson that we want to learn from this. So, what do? Let us come back, and what I want you to do is to look at this picture. So, we are going to look at the fusion number again. So, what are we going to do now? What we are going to do now is to repeat the same exercise with respect to carbon. And remember, 12 carbon has 6 protons and 6 neutrons. So, I plug in the number again, and carbon has a very beautiful number for its mass, which is 12 atomic mass units. We have to pair respect to what? The significant digits. I have written that many significant digits. And if you people remember the error analysis which was taught to you in the 11th standard, you were told whenever you have an exact integer and whenever you are multiplying it with another number which is not an exact number, the number of significant digits that you attach to the exact number will be equal to the number of significant digits that are there in the measured quantity. So, that is what I am doing. I am putting all these 6 fellows because there are 6 significant digits or 7 depending on whether you count this or not. So, if I calculate my delta m, it turns out to be 0.056 atomic mass units, and now you see the energy difference is 54.64 million electron volt. Whereas, how much was it for the helium? If I go back to helium, it was 28.3, so this is roughly twice. Is that right? For helium, it was 28.3 million electron volt, whereas for my carbon, it is 54.64. Therefore, if perchance there are the right conditions in the interior of a star, maybe inside the sun, if not inside the sun, another star, is that okay? If there are right conditions, you should be able to produce even more energy, which will be 54.64 MeV through a cycle. Now, that means I have to again work out how, starting with protons and neutrons, you should be able to synthesize the carbon, and that is called the carbon cycle. What I showed you was the helium cycle, but what follows is the carbon cycle. This great physicist Hans Bethe, he has contributed enormously to many number of fields. He is a Nobel laureate. He was the first person to realize that there could be a carbon cycle inside the sun, and he worked out the full dynamics. We are not doing dynamics, we are only doing bookkeeping. Is that right? We are only doing energy auditing. He worked out, is that okay? And that process is shown in this cartoon. I do not want to spend too much time. As I have shown you, the credit is in the Wikipedia, is that okay? The final process carbon, 12 carbon is shown here. Is that okay? So, helium, nitrogen, 13 carbon, so on and so forth. Okay? You can go and look up the book. The temperature inside the sun is of course 1.5 into 10 to the power of 7 Kelvin. I am just giving you that information because I want you to find out whether such a process is possible inside the sun or not. Is that okay? That is what I want you to do. So, if you did that, is that okay? Even more energy will be produced. And what will happen? As the temperature in the core of the sun keeps on increasing, you can keep on producing more and more nuclei. So, now let us look at our earth, which has so many elements. After all, they were all discovered here: molybdenum, phosphorus, silver, and there are this whole range of rare earth metals. Then you have uranium, using which you make either a fission bomb or a nuclear reactor. Then you have polonium, you have thorium. Where were they all produced? That is a good question to ask. And we say they were all produced in the interior of the stars. If you look at the human body, we have lithium, we have magnesium, we have traces of phosphorus, we need all of them, right? So that means every element that inside our body, apart from the earth, after all we are made of the earth, were all synthesized somewhere in the interior of a star. And as Carl Sagan said in one of his presentations, he made a series called Cosmos, a TV serial. He says, for that reason, we are all products of stars. Everything came out of the stars, And for us, our big granddad is actually the sun. Is that okay? That is something that we have to remember. So, this is the carbon cycle. Now, there is an interesting thing. So, greater the temperature, what is going to happen? Greater the energy released, and greater the energy released, that means the lifetime of the star goes down, because as you keep on losing your energy, eventually you are going to either form all of it as a carbon or oxygen or iron, let us say. After that, it cannot produce any more energy. So, that is what we are saying. So, if you look at the binding energy per nucleon, it tells you, that is the reason why I put it here. That means that as you keep on producing more and more stable nuclei, your capability to produce energy decreases, and at some point when you stop producing energy, that is the death of the star. So, I want to conclude this lecture by showing what the lifetime is, and this curve shows it. So, what I shall do is just look at these numbers. In the next lecture, I will start with this and tell you how when the star becomes more and more massive, actually its lifetime becomes smaller and smaller, and then I will go on to discuss radioactivity, which would essentially conclude your course as far as whatever our mandate was, and we will take that up in the next lecture.